Okay, thank you. Okay, so I'm not used to start talks this late in the afternoon, so I'll try to go slow. Okay, so yesterday I talked to you about the problem that we will be interested in, which is the domino problem, and the fact that there is no algorithm that can decide, given some tile set, if this tile set tiles the plane or not. And we will not prove the result today, we'll prove it on Thursday. But before, if you want to prove a theorem like this, you need a definition of what an algorithm is. So what I will do today is I will try to give you a definition of what is an algorithm. So if you already know a lot about computer science, you can probably sleep. There is nothing new there today. But otherwise, I think it will give you some idea of how you can define an algorithm. Okay. So first, if you look in the literature, there are a lot of different definitions of what a computable function is. So all of it was done nearly at the same time in the 40s. And there are basically three different definitions. The first one is a definition with a program. So you define what a program is, and then you define computability as things computable by programs. There is something which is quite different, which is you can define functions that are computable with a series of axioms. So you are given some axioms, and the set of all functions you can compute with these axioms are the computable functions. And you can do it with what is a mechanical device, which is what Turing did. So this is a very different definition. So either with a program, either with a mechanical device, either with a set of axioms that you have to satisfy. But what is very important is that all definitions you can think of for a program or for an algorithm are the same. So you obtain exactly the same computable functions. So it's important that you do not obtain the same notion of algorithm, but you obtain the same notion of what is computable and what is not computable by some computer or by some human being. So this is a Church-Turing thesis. So all reasonable notions of algorithm you can conceive of give equivalent definitions of computable functions. Not of algorithm, but of computable functions. Okay, so what is very important and might be, it's quite silly, but it's very something that can lead to errors. What is important is that computability is only defined when you take as input integers and nothing else. So of course, if you can take as input integers, you can take as input finite words, because a finite word is not that different from integer, but you do not take, for example, infinite things as an input. Okay? If you want to speak about the computability of something, this something should be definable by integers, by finite words, but that's it. So trees, for example, are okay, but no infinite things, no real. You cannot give a real to a program. A real is an infinite object, it's not a finite one. So it's very important that you need encodings. Every time you have to deal with something, you need to encode it into integers or finite words. The encoding is not very important, but you have to think that at some point, some encoding should take place. Okay, so the model of computation I will use is something very classical. So again, if you know about it, everything I will say is completely classical. So what I will use is something which is called the Turing machine. And the Turing machine is some abstract device that was introduced by Turing. And the goal of Turing was to model what the human being, the brain of a human being is doing. So if you look at the article by Turing, he tried to think, so how do I think? What am I doing when I'm thinking? And try to formalize it into something which is mechanical. And this is what you obtain. This is the model of the Turing machine. So again, as I said before, there are many different models of computation, many different ways to define computation, but you will see that for many examples, the Turing machine is the object that you need because it is the easiest way to code things, to code into things. Basically because it's mechanical in some sense. Okay, so first, what is a Turing machine? So you have something which works in discrete time space. So you have step 0, step 1, step 2, step 3, etc. And so this is just the beginning of the definition. At each step, what you have is something which is on a workspace. And what is a workspace? It's just a one-dimensional tape. So a tape filled with symbols in some alphabet. So the alphabet will be called A or sigma. And your tape can be simply infinite or be infinite. It really doesn't matter, but you have to take some convention. So first, here is an example. So you have your tape. So of course, this is only a finite portion of the tape, but you have to think of it as being be infinite or simply infinite. And you have some letters on the tape. This is the first part you need for a Turing machine. You first need a tape. So just an infinite collection of letters organized in an infinite or be infinite row of cells. Okay, then the next thing you need is some scanning device. So the scanning device will be put somewhere on the tape and will be able to read and write what is on the cell it is currently on. So this scanning device is usually called a head. And so what can you do? So first, in the scanning device, you will have some finite state, which is the internal state of your device, like this. So it means my head is at this position, and it has 1 as an internal state. And the next thing you need to know is what can this scanning device do. And actually, you can do 3 things depending on 2 things. So first, it's a scanning device, so it can scan the letter. It can scan the letter and see that it is an A. It has an internal state, and depending on both these elements, it can decide to change the state, to change the symbol, and to move. Okay? So you just have access to 2 things, an internal state and a symbol, and you can change the state, you can change the symbol, and you can move. So formally, if you want to define it, you need something like this, just a function, which takes as an input the old state that will change and the symbol that you read, and as an output, so this function gives you the new state, gives you the new symbol that you write, and something which represents the movement. So here the movement is just left or right. So this is, formally, if you want to define a Turing machine, you need some function like this that say, okay, given some state and some symbol, this is what I will do. I will go to some new state, change the symbol, and possibly move the state, the head. Yeah?
And can you stay?
In the example, it will not stay in the same place, but you can change. So there are many things you can change the definition. They are not important. They give exactly the same model. Well, model with the same properties. Okay, so here is an example. So this example is just a very bad example. The table doesn't represent anything, just a table that I put at random. Okay, so what do I see? So I see that first I have my scanning device, which is my head, which is on the symbol A, and with state 1. So what do? I look in the table. I see that, okay, if I am in state 1 and I read letter A, then B to right. So what does it mean? First, I will change the A into a B. Then I will change the state into a 2. And then I will go right. Okay? And then I do the same. So now I'm there. And I'm in state 2. I read a B. So what should I do? I should write an A, stay in state 2, and go right. So again, if I'm there, I will go there, and then here. And then again, it's the same case. So I'm in state 2, I read an A, then I will write a B, go to state 0, and go back to the previous A. And I continue afterwards. Okay? So again, this example was just put at random. There is nothing to understand in this example. Just out. Okay, if you look at what I am doing, I decided that when something moves, it is the head that moves. Dually, you can think that actually the head is fixed and that the tape is moving. What does it change? Well, it changes when you look at it as a dynamical system, the dynamical system is quite different. So it has some different properties. So depending on the context, you have to think of the head that is moving or the tape that is moving. Usually it will be the head. Okay, so if the head is moving, this is what you have. If you want to look at what is the function at one step of time, you start from this kind of thing, and of course it is a dynamical system. So what is a configuration? You need to know what is on your tape. So just for each position of the tape, what is the letter on the tape. You need to know the internal state of your scanning device, and you need to know the position of the head. So that's one way to do it. And again, you can have simply infinite tapes, so just replace the integers by the non-negative integers if you want. That's exactly the same. So that's one way to do it. Again, the other way to do it is just fix the position of the head and move the tape. So in this case, you'll have something like this. You don't have to specify where the head is because the head is not moving. The head will always be at position 0. So it means that now it's an easier space. Of course, to do it, the tape should be infinite. It doesn't make sense for a simply infinite tape to do it, but this is another way to write. Okay. So now we have a definition of a Turing machine, and how do you compute with it? Well, what is a computation? A computation, you have to start with something and then get something. So what do you do? First, you have to write the input. So you will first start by writing the input on the tape, and then you will have to somehow reset your device so that it begins, so that you can start the computation. So what do? You reset the head so that it is at the beginning of the tape, so at position 0 on the tape, and the internal state is fixed to some specific internal state that marks the beginning of the computation. And then you use the mechanism I spoke about, so you run the Turing machine, and at some point, maybe, it will stop. Why will it stop? Because there will be some specific state of the scanning device that says, okay, I'm done, I've done everything I want to, and now what I will do is I will read what is on the tape. So I put the input on the tape, I just launch the machine, and then maybe at some point it will stop, and if it stops, I will read the output. Okay? So now I will try to give, okay, so first, so what does it mean? So formally what I have is some function that map input to output. So inputs are just words from some alphabet, and output are some words from the same alphabet or some different one, if you want. So just a function from input to output. But what is important is that it's not a function, but actually a partial function. Because it's possible that the machine will never reach the ending state, the halting state, and then it will run forever. So actually it's a partial function from input to output. So it may or may not stop and give you an answer. Okay, so what is really important and what is the essence of the Church-Turing thesis is that this particular model, which seems like something which is very mechanical, actually can simulate any algorithm you can think of. So this is not really a theorem because you cannot give a theorem about this, but basically it's some observation that any algorithm you might think of can be done in this model. So now we'll say that something can be computed if it can be computed by this model. So this model can find the answer to your problem in some finite time. Okay, so let's look at some example. So this is a real example of a Turing machine that is doing something. Okay, so here is a table. So I have to specify the initial state which will be 0. I have to specify the halting state which will be B. And I say, okay, this is a real example. Let's say that I start from 0, 1, 1. What is the output? Okay. Okay, it's not that easy. You can write the table like this. So it's exactly the same table in a different way. So how does it work? So the vertices are the states, and I will put an edge that corresponds to what I call the transition, so the different actions you can take from this state. So for example, I don't know which one, this one. say that if your scanning device is in state 6 and it sees a 1, then it will write a 1, it will go right and go to state 9. Okay? Okay, it's still a big graph. Okay? So you're not supposed to understand the graph. But now we can try to do it just bit by bit and see what this entire Turing machine is doing. So for this particular Turing machine, it turns out that to understand what it means, you have to see the input as numbers in binary, and they are represented in the not usual order, so the other order. So you start with the least important bit. So 0, 1, 1 is 6, okay, and not 3. So again, to understand this machine, this is a hint I am giving you. You have to think of it as doing something on numbers. Okay, so now if you look at the machine, it starts on 0, so let's look at what is on 0. Okay, so you see that on 0 it goes to 1, doing nothing. You just read a B and write a B and goes to the right, it's not important. But what is happening on 1? Okay, you see that on 1, it is written that either you see a 0 and then you replace it by a 0, you go right, and then you do something. Or you read a 1, you replace it by a 0, you go right, and then you do something else. So it means that this state 1 corresponds to what we would call in a programming language some kind of test, conditional. Okay? So if the input begins with 0, do A, else do B. Okay. So let's look at our input. Our input is 0, 1, 1, so it begins with a 0. So let's look at A, so the part on the top. So this is A. So again, I'm entering at 2 because I'm coming from 1. And okay, I will just look at state 2 and then there is an A prime somewhere above it. So what is state 2? State 2 is a very easy state. So what does it do? If you read a 0, you write a 0, you go right. If you read a 1, you write a 1, you go right. So basically, you are just going right, doing nothing. Until you see a B, a big B, that denotes the fact that you are at the end of your input. Okay? So what does this state 2 do? You are starting from the origins, and you are reading all the cells, doing nothing else until you reach the end. So basically, this is just a go to the end of the input. This stage just say, go to the end of the input and then do A prime. Okay, so now what is A prime? So A prime is this part in the big rectangle. So this one is not that easy to understand. What is? It enters at 3. It enters at 3, and then it's done something. So remember, if you look at what we add, so we go to the end of the input, and we go left, which means that we are at the rightmost symbol in your input. So in 0, 1, 1, we are at the 1. Okay? So rightmost one. Okay. Okay, this part starts to become a bit harder to explain. So basically what you have to understand is that starting from 3, you either go, if you read a 0, you either go to something that I called R0 or something that I called R1. So if you look at the transition, at the graph, you see that every time I read a 0, I will go to state R0. And every time I read a 1, I will go to state R1. So basically, the state R0 and R1 somehow remembers what I just read. Okay? And now if you look at the outputs, so if you look at the inputs, you see again that R0 is just where you go if you read a 0. R1 is where you go if you read a 1. And then now you look at the output of R0, and you see that, if you are on R0, the output is always a 0. And if you are on R1, the output is always a 1. So what does it mean? Basically, it means that you enter in R0 if you read a 0, and the next time you will write a 0. And if you look at what the head is doing, the head is always going left. So what you are doing is actually shifting the input. Okay? Because you write what you read just one step before. So basically, you are just shifting the input. And then when you are at the beginning of the tape, you will encounter a B, and then you will go back to 1. Okay? So if the input begins with 0, go to the end, shift the input to the left, and go back to 1. Okay? If you want to look with numbers, if n is even, divide n by 2, and then go back to 1. Okay? Okay, so at some point, so you are starting with 0, 1, 1, which is 6, which is even. So at some point, we'll go to 1, 1, which is 3, which is odd, and then we'll go to B. So this is just the beginning of B. So you enter B at state 6. And what you see that, okay, if there is nothing else after the initial one, I stop. Because B is the B at the top left is my final state. So it means, okay, if at some point my integer n is 1, I stop. And otherwise, I will do B prime. Okay, so if n equal 1, output 0 and alt. Otherwise, do B prime. And okay, as you can suppose, this is what B prime will be doing. Okay, so B prime will multiply n by 3 and add 1. So this is B prime. Okay, so what you have to understand is just this part. This is actually a multiplication by 3. And there are 3 different states because there are 3 different carries when you multiply by 3. Either you have a carry of 0, a carry of 1, a carry of 2. And these particular states are just the way you are doing a multiplication by 3. And now you look back and you see that actually what is important is that when you start from 6, you go to the exact state that say I actually have a carry of 1 at the beginning, because it's 3n plus 1. So this is what this part is doing, and actually I don't know if, yeah. And the part with A is just to go back, because you are going to the right of the input, so now you have to go back to the start of the input. So this is what state A is doing. Okay, so this is what my Turing machine is doing. It starts from n, which is a number coding in binary, and what it does, it will do the correct sequence starting from n. So if n is even, it will divide it by 2. If n is odd, it will multiply it by 3, add 1, and it will keep on doing it until at some point it reaches 1. Okay? So we don't know if it will always happen, of course, but this is what this Turing machine is doing. So let's look at it again. So this is 0, 1, 1. So what does it do at first? It will shift the input. So this is what's happening in one step and a few steps. And then 1, 1 is odd, so it will multiply 1, 1 by 3. So 1, 1 is 3. 3 times 3 plus 1 is 10. So 10 is 1, 0, 1, 0. This is what you'll obtain. Okay, and then you go back at the origin. This is even, so you divide it by 2. You obtain 1, 0, 1. It is odd, so you multiply it by 3, etc. Okay? So this is an example of a Turing machine. It's a complete example. There is no mistake in it. It really works. That implements the correct sequence. And alt, if only if you alt, you will reach 1 starting from n. So it's not completely accurate, because if you start from 0, for example, it will not alt. But if you start from a real binary integer written correctly between 1 and the infinite, it will work correctly. So this is a real example to convince you, try to convince you, but there are still many quotes there, that with Turing machine it is easy to code arithmetic, so plus, multiplication, etc. You can have something that looks like subroutines. When I have this A, this B, this is just what you will have subroutines in the programming language. And I have everything I need to do flow control. I have if statement, I have while statement that I can simulate with my states. So as I have arithmetic subroutines and while and if, I think you can be somehow convinced that I can do anything I want. Okay? So this is just an example to try to prove to you that anything I want to do with an algorithm, I can do it with this model, even if this model looks quite painful to code with. That's true. You are not supposed to write programs for Turing machines, but you can. Okay. So again, the important part is that Turing machines are something that are quite mechanical, but if you do it correctly and if you take a lot of time, you can program things in it, which means that any algorithm can be programmed in it, at least in theory. Okay, so now let's see what this Turing machine is and how you can use it to prove theorems about tilings, because we are not interested in Turing machine, but in tilings. Okay, so let's remember what is our goal. So our goal is to prove that there is no algorithm that can decide if some given tile set tiles the plane. That's what we want to prove. And remember that what I call a tile set is something that is given by Wang tiles, and Wang tiles are just squares with colors on the border. So how do you use the concept of a Turing machine to prove it? Well, so first, now you have a definition of an algorithm. An algorithm is something that you can do with a Turing machine. But now, if you want to prove that there exists no algorithm for this, you need first to try to come up with some problem which is hard for Turing machine, which is that you cannot do with a Turing machine. And then you try to translate this problem into a problem with tilings. So this is the main problem we will use, which is the halting problem, which is a problem to decide, given a Turing machine, if this particular Turing machine halts. So again, if you want to look at this problem, so this problem took the Turing machine as input and want to know if this Turing machine halts. So basically, you are feeding a Turing machine to the Turing machine and try to see if it can simulate it and know if it halts without actually simulating the Turing machine. Because if you simulate it, you will possibly run an infinite number of times, and then you cannot say, yes, it will not halt. Or no, it will not halt. Okay? So how do you prove that this cannot be done by a Turing machine? So first, here is the exact statement, because you need the statement to be exact. My algorithm take as input a Turing machine M as some integer n, and what I want to know if the Turing machine M will halt on input n. So as I said before, to be able to do it, I need to have an encoding of Turing machines into integers. Okay, I will not give you an encoding, it's not important, but again, a Turing machine should have on its tape integers or finite words, not Turing machines. So you have to have an encoding of Turing machines into integers, but that's easy. It's a finite object, so you can encode it. Okay, so how do you prove it? Well, it's easy, because remember that a function is computable if it can be given by a Turing machine. A Turing machine is a finite object. So as it is a finite object, it means that there are only countably many Turing machines. But there are infinitely many functions. So first, if you know your counter argument, you know that you can prove that there exists something which is not computable by a Turing machine, just by using counter diagonal argument. So this is what you obtain. So first, let's write m of n for the machine, the function computed by the nth machine, and I will exactly do what you do with counter diagonal process. So I will say that I answer 0 if the nth machine does not halt on input n, and I will not halt if it halts. So basically, if it halts, I will not halt. If it doesn't halt, I will halt. So it's exactly the same as +1 in the counter process. Okay, so let's look at this function. So this function, by definition, cannot be computed by a Turing machine. But now if you look at this, you say, okay, but this looks like an algorithm. Okay? If we can turn this f into an algorithm, we will be able to prove that this f is in my list of functions, which is not possible by counter argument. So it means that somewhere in this, there is something which is not computable. And the only thing you cannot do in this is if you look at the definition of f of n, well, the first thing you need to know is to know if mn of n halts. So it means that you cannot do it. Okay? if you were able to decide if the Turing machine halts, you will be able to transform this into a function, and then this function would be computable, and this doesn't work by counter argument. Okay, so this particular function cannot be computable, which means that somewhere inside there is something that cannot be done by a computer, and that's basically this part. If you can do this part, if you can decide if the machine halts, you're okay. Okay, so this is the first example you have of an undecidable problem, which is quite specific. And what you will use usually is a different version, which is a bit simplified. Here I do not have any input. So I just have one Turing machine and the input will be empty. The proof is more or less the same. I will not go into the two lines. But basically, this is what we will start with. Okay, so now this is our goal. Now we have something that we cannot find an algorithm for. And now we want to say, okay, but maybe if I can do this with tilings, then this means that with tilings I cannot do it. I cannot decide if a tiling exists because I will somehow being able to solve this problem. So that's what we want to do. So we want to build an algorithm that does the following. You start from a Turing machine, you will build some tileset tau, and you want to do it in a way so that deciding if tau tiles the plane is the same as deciding if the Turing machine halts. Because if you do it, again, as you cannot decide if a Turing machine halts, it means that you will not be able to decide if tau tiles. So that's what you want to go. But then you have to think a bit and see that actually that's not exactly what you want to do, because in both problems there is a hard part and there is an easy part. It's easy to see that a Turing machine halts. You just have to wait, and at some point you will see that it halts. It's easy to see that a tileset does not tile the plane. You look at bigger and bigger square, and at some point you will see that there is no tiling. So these two parts, the easy part of the first problem should correspond to the easy part of the second problem, which means that this is the transformation you should have. So at the bottom, you should do the transformation in a way that you will tile the plane if only if your Turing machine does not halt. So again, the Turing machine will not stop if there is a tiling. If there is no tiling, the Turing machine will stop. Okay, so that's our goal now. So we want to somehow transform a Turing machine into a tileset so that knowing if the Turing machine halts is the same as knowing if the tileset does not tile the plane, to be exact. So now the question is how to transform a Turing machine into a tileset. And actually, it's actually very easy. There is a bit of a problem, but it remains quite easy. So to see why it is easy, you just have to look at this. So what is this? It's just the exact same computation as before from my Turing machine that I put in some kind of diagram. So I put the symbols on a grid. Okay, so it's usual to have the time goes up. So this is, you start from there and you go to the top. So this is the exact same Turing machine as before. I just write each step on one row. And if you look at it, it's almost like a tiling. What do I mean by this? It means that actually everything that happened can be given by local constraints. You just have to look locally at what you see to see what you will have at the next step. So what it means is that if I look at this, it's very easy to convert it to this. Okay? So again, everything is exactly at the same place. You see that this tile A here corresponds to the symbol A here. The B here is the B there. And this is how you will represent the tape, the head. Okay? You will see that in each of your rows, one very specific cell will be marked with some state, and that this state can either go right or go left, which corresponds to the two possible movements of my head. So how do you do it formally? You just need 5 tiles. That's it. Well, there are many tiles, but just 5 different kind of tiles. So the first one on the top right is just a tile that says this is the letter A. And you see that I put the Wang constraints, the Wang constraints that say that if I have a tile with an A, then I should have an A on the top and an A on the bottom. The two tiles at the bottom are just to represent the state of the head. And this says that, okay, if at some point I am in state Q and I read an A, then I will either go left or go right. So this is the case where you go left. This is the case where you go right. So you see that somehow the Q state will be transmitted, will go left or right, and that the symbol has changed. Okay? If you look at the top, there is no A prime, and not an A. So it means that with this particular tile, you have actually said, I was in state Q, I read an A, I will go to state Q prime, I will go left, because the wire somehow is going to the left of the tile, and the A will be transformed into A prime. Okay, and then you have to use these tiles that are on the top just to have this Q prime goes to the next cell. Okay, so again, this is exactly what you have. So this means I am in state B, I'm in state 2, I read the B, and then you have this wire that says, okay, I am currently going left, and this B will be transformed into an A. So this will be done at the level of the north side of the Wang tile. So you just need 5 basic kind of tiles to do it. Very easy. So again, these are really Wang tiles, okay? This is really a tile with A on the top, A on the bottom, nothing on left, nothing on right. There's no cheating there. Okay, so what it means is that if I do this, I have the property that every infinite computation of a Turing machine gives rise to a tiling of the upper half plane. Okay, so it's not a tiling of the entire plane, so you have to fill up the bottom every way you want. But anyway, you still have a tiling of the upper half plane. So that's one direction of what I want, because it means that if my Turing machine tiles the plane, if my Turing machine does not halt, I will have a tiling of the plane. Okay? It is good. The problem is that, of course, it's not that easy. That's a big caveat we will have. Not every tiling of the plane corresponds to this. So even if you look just at these 5 kind of tiles, you can obtain things that are not a computation of a Turing machine. So that's the big problem. And that's why we will need an entire course on Tuesday to try to find a solution to this. So what can happen? Well, 4 different bad behaviors can happen. So the first bad behavior is that, okay, as the head is present only at one cell in each row, actually it might be possible that there is no head at all. Okay? Nothing forces an head to be there. So maybe there is no head at all. Actually, if you look at how I defined it, it's also possible to have an infinite number of heads per row. So maybe 2 heads per row, or even an infinite number of heads, which is not something that you want, again. If I want to look at the computation of a Turing machine, usually start from some initial state and from some input. I have no way to give the input. I cannot say what it started from. And of course, as I used blank tiles to fill the rest of the plane, it's possible that I have only blank tiles and not even some cells somewhere. So that's basically the 4 different kind of bad behaviors I want to have. So now what I would want to try is trying to erase these bad behaviors. And that's not easy. And actually, you can even say that it's not possible, in some sense. Okay, but what is interesting is that if even one row is correct, then everything above it is correct. If you look at how I defined everything, it's quite obvious that if one row is correct, everything above it is correct. That's something. So it means that if I have some way to force just one row to be correctly tiled, to correspond to something that is a Turing machine, then I will have one, because everything above at least will be correct. So that's my next goal. And this is actually easy to force. Just 4 tiles. Okay, so these are my 4 tiles. So basically my 4 tiles say that I am in the initial state. So this is the second tile I have. And the tile on the left and the tile on the right just say that, okay, everywhere I have B, which represents the blank symbol. That's easy. Okay, so this is technically wrong because the color on the left tile should be different from the color of the right tile. But anyway, the symbols are good. With the symbols, it's okay. So if I have this tile, the tile on the top center, then you will see that having this tile forces your configuration to have an infinite number of B at the left, an infinite number of B at the right, and to have in the middle, let's say, these particular tiles that say that you are starting the computation because you are in state Q0 with an empty input. That's exactly what I want. And okay, so this is my row, and I can fill what is below with this white tile. So I have this white tile to fill the bottom of the plane. So again, if I suppose that this tile exists, that this tile appears somewhere, then I will have an entire configuration with blank symbols and a head at some position, nothing below it, and above it, if you look at the rules, they force the tiling to simulate the Turing machine. So I obtain something which is not what I want, but it is quite close, which is what I have on the top. So if I look at the tile T, which is the tile on the top center, there exists a tiling with T, with this tile, if and only if the Turing machine does not halt. Okay? So this is not what I want, but it is quite close. So what I have proven is not the undecidability of the domino problem, which is, again, quite hard and will need at least 1 other hour. But I have proven something else, which is quite interesting in its own right, which is that you cannot decide, given a tile set and some tile T, if there is a tiling by tau that contains T. So maybe there is always a tiling by tau, but deciding if there is a tiling by tau with the tile T at some point, this is something that you cannot decide. There is no algorithm for this. So again, I don't know if, yeah, okay. So why? Because you are starting from your Turing machine, you are encoding it into your tile set. And so if the Turing machine does not halt, there exists a tiling with T. You just look at the computation, it will give you a tiling. And conversely, if there is a tiling, as we saw, the only way the tiling can exist with this particular tile is to simulate the Turing machine, which means that the Turing machine should run forever. So the Turing machine does not halt if and only if there exists a tiling with this tile T. Okay, so that's nice. That's the first theorem you can obtain, which is a theorem which is due either to Wang or to Karl Moore-Wang, which is 2 or 3 years before Berger. It's just beginning of the theory of tilings from the point of view of computer science. Okay, in what follows, we will need some other theorems that are just variants of this one. How to prove this theorem is not important, just very variant. So the first one is instead of saying that you tile the plane with a tile T, it's also undecidable to know if you tile a quarter of the plane with a tile T at the bottom of the quarter of the plane. This is also undecidable. It's exactly the same proof, but now you have to use a Turing machine with a simple infinite tape instead of a B infinite tape. So this will be useful because more or less that's the problem you want to start from. And now to do something different in the rest of the hour, I will use also this theorem that says that given 2 tiles, T1 and T2, there is no algorithm that can decide if there is a tiling that contains T1 and T2 in the corner of a square. So T1 at the bottom left, and T2 at the top right. So again, it's exactly the same proof. There is nothing different about it, but this is what we will use in what follows. Okay, so question you can ask is, okay, what is missing? We have a way to encode Turing machines into tilings, but now you have to force the existence of this tile T. And Well, there are two ways to do it. So the first is to find a way to force the tile T to appear, and then it's okay. And there is another way we will use next time. It's to change the coding. So the coding we use of Turing machine is quite easy, it's quite nice, but maybe with another coding you can guarantee some other properties. Maybe you can guarantee that there is always an head. Maybe you can guarantee that you always start from an initial input. Maybe the problem is the coding. And actually, you will see next time that with something which is not that easy, which is quite subtle, you can change the coding to be certain that you have an head. So you will have no guarantee that you start from initial configuration. You'll have, but you have a guarantee that what you observe is some kind of computation. Maybe not starting from initial configuration, but at least it's some kind of computation. So this is what we will do next time. Okay, so what we'll do this time, so there's still a bit of time left. We look at some problems that we can already solve with this method. So what I did before, I spoke about the problem of, is there a tiling that contains some tile T? And now the problem I will look at is there a tiling that is periodic? And I will prove to you during the what remains that this cannot be solved, so there is no algorithm that can decide if there is a periodic tiling. Because this proof does not need the whole machinery that we will see on Thursday. And so this is very, very much easier. So this is a theorem which is due to Gurevich and Koryakov, which was done after Berger, but actually you can prove it just, not really just, but basically from basic principles. Okay, so how do you prove it? So this is what we want to prove. We want to prove that, okay, maybe the domino problem is hard. Maybe we will not have time to do it today, so we'll do it on Thursday. But we'll do this problem, which is there a periodic tiling? And we'll prove that this one is undecidable. Okay, for this, we need to assume that there is an aperiodic tile set. So you have seen a lot of them in the literature, in the talks. So we'll suppose that there is one of them. We do not need to know what it looks like. We just need to know that there exists an aperiodic tile set. So what is an aperiodic tile set? Again, it's a tiling with no periodic tilings. So if I look at periodic tilings, I see nothing. Okay. And then this is what I will add. So black is a new color, and I will add every Wang tile of this form where yellow and, let's say, pink are every color that can appear in my set of Wang tiles. So I look at all Wang tiles that I already have, and I will put this tile, so black on the top, black on the bottom, and any two colors that can appear. So what are the periodic tilings now? They look like this. Now you can have periodic tilings, because now you can have these black rows that go to the infinite, and that black columns, and that will somehow divide your plane into columns of some size, some arbitrary size. So this is what a periodic tiling might look like. Okay? So you have a black column. Okay? Because if you do not have any black column, you have as your tile set is aperiodic, there is nothing. There is nothing periodic. So as you suppose that you are looking at periodic tilings, there should be at least one column of black. Okay? And then many columns of blacks in the period, you don't know anything about it, but at least there should be one column of black. And the next step we want to do, we want to organize what is inside each two columns of black into squares. So that's our next goal. So first, just by saying I'm looking at periodic tilings, I know for a fact that I have these black columns. That's the first step. And now I want to somehow do rows. So transform my just columns with void, empty inside, into squares. To do it, I want to do something like this. I want to do something like a particle that is red on the picture, that somehow goes from left to right and teleports once it's at the right. So I want to do something like this. Okay? Okay, so why Because now if I look at the moment when the particle teleports, it will give me my squares. So now the question is, how do I do this? Well, remember what I did yesterday. Yesterday, I tried to represent tileset as transducers, as automata. If you look at what you want to do as an automaton, it's quite easy. So first, you have to look at them like symbols. So the particle, the red particle will be a 1, the void will be 0, and at each step, you have something which is a lot of 0, a 1, and then a lot of 0. And what you want to do is just shift the 1. So for this, you need either the transducer on the top or the transducer on the bottom. So what is the transducer on the top? It just shifts the 1 step to the right. So first, from Q0, you read 0. You read a lot of 0. And at some point, you will see the particle. You will replace it by a 0. And in the immediate next step, you will write the particle. So that is what this transducer is doing. It's just, basically, if you start from 0, 0, 0, 1, you will have 0, 0, 0, 0, 1, just shifting the 1 to the right. And then, of course, you need another transducer that corresponds to what you should do when your 1 is at the top right, and that you will have to put this one in the left. Okay, and this is what you are doing. So basically, you are saying, okay, in the particular case, so this is Q4, Q5, where I have a lot of 0 and the 1 is at the very end, I will replace it by a 1 at the very beginning and a lot of 0s. Okay, so this is something which is non-deterministic. Okay, you have to know that at some point you will see the 1 at the end to be able to do this particular transducer. Okay, so with these 2 transducers, with these 6 states and these 7 edges, what you are doing is essentially you have written a transducer that takes your 1 and just put it 1 step to the right. And then you just do it with tiles. And now you see why some of them are colored with gray colors. Just a convention, I could have colored them blank, like the other one. But then, now this is what's happening. Okay? You have these gray squares that correspond to the moment when the 1 goes from right to left. And then you see that the 1 is going again to the right. Okay? To do it, you need a few tricks. So these are transducers, but these are transducers with initial states and with final states. So you need some rules, which are what you will put on the black tiles to ensure that you start from an initial state and that you end in the final state of your transducer. So you have to, so Q5 is one of the possible final state, Q3 is one of the possible final state, and again Q0 and Q prime not as the 2 initial states. And now you are very much done. Because now, instead of your structure which was nothing, you first, just by saying, I'm looking at periodic things, you have given black columns. And then by using this transducer, so using this approach of tileset with transducers, you have somehow made rows. So now you have split your entire plane into squares. You don't know anything about the size of squares, but at least you know that there are squares everywhere. There should be squares because you cannot tile without these black tiles. You cannot tile periodically without these black tiles. Okay, so this is what we have done. And now it's almost finished. Yeah, as you see. It's almost finished because the only thing you have left, you just have to put what I did before, the entire thing with the Turing machine, inside each of these squares. Remember what I said before? You cannot decide if there exists, given a tile set, if there is a tiling of a square with T1 at the bottom left and T2 at the top right. So now you just have to put this particular tileset tau inside each square in a way that you guarantee that T1 will be at the bottom left and that T2 will be at the top right. Okay, so this is what you should do. So you start from a tileset tau, which is not what I've done before, just another tileset tau, and with two tiles T1, T2. And this is what I will do. So every tile inside the square will be a tile of this tileset. So this is something that I am superimposing to the previous picture. I have another layer somehow of tiles. And I will say that, okay, the rules is that I have to follow the rules of the tileset tau, except on the border. On the border, I can do anything I want, because basically, I want everything in two different squares to be independent. So at the border, I have no rules at all, which basically means that tiles on the border of squares can do anything with good colors. And then I should ensure that on the bottom left, I have T1, on the top left, I have T2. And if you look at the picture, you see that this particular tile appears only once in every square. So it means that this particular tile is a way to ensure that T1 appears. Okay? You will say, okay, in top of this particular tile, I should see T1. And the same thing, this particular tile, which is actually at the top of the computation, so this one, if you prefer, only appear once in a square. So we will say, okay, in this particular tile, I should see the tile T2. And if you do it, you're done. Okay, why? Well, suppose there exists a periodic tiling. If there exists a periodic tiling, then this tiling, as we saw, should contain black columns. These columns should be divided into squares, which means that this tiling contains a square. Somewhere in this infinite tiling, there is a square. And this square, by definition, contains the tiling of tau with T1 at the bottom and T2 at the top right. Okay. And now, suppose that there exists a tiling by a square with T1 at the bottom and T2 at the top right. Then you can use this square to tile periodically by putting this square everywhere and just using this particle stuff to form squares, and you're done. Which means we are done because we have proven that it's equivalent to saying there exists a tiling of period n and there exists a tiling of a square with tau with T1 at the bottom and T2 at the top. So it means that these two problems are equivalent, so it means that neither of them, as one of them cannot be solved by Turing machines, the other one cannot be solved. So we have proven the undecidability of the periodic domino problem. And now what remains to be done next time is to finally try to go to the interesting case, the hardest case, which is the proof of the undecidability of the general domino problem. So no periodic problem, no problem with some given tile at some point, just a general problem. Okay, thank you.
Questions?
Should really have come on front if you want to ask questions.
I have to admit I'm getting a little tired, and maybe you have already answered my question, but I ask it anyway. So do I understand the result correctly, that there is no algorithm which solves this decidability problem for all given sets of time, right? Correct? Is that that's the result? But however, for any given set, could it be that there is an algorithm? Okay, so for a given set, the problem is that if you look at it from the point of view of algorithm, the answer is either true or no, yes or no. So it means that it is a decidable problem because it's a problem on one instance. So you cannot say it like a decision problem somehow. Basically, when you say that a problem is undecidable, you are saying that given an input, you cannot answer. If you have no input, then there is really no problem. You can. No, I'm sorry. Maybe I didn't understand. So given a set of tiles of prototypes, tiles. And you want to know whether there exists a tiling.
Yeah, but again...
So if I give you a concrete set of tiles, like...
Yeah, if you are given me a concrete set of tiles, for one given set of tiles, the answer, again, is either yes or no. So from the point of view of computability, this is a decidable problem because it's a problem on one particular input. I don't know the answer. I don't know myself if the answer is yes or no, but there is two programs. One that answer yes, one that answer no, and one of them is correct. Okay? This is very important.
So what is the program for the no answer? A finite program for the no answer?
Oh, so again, if you have no input, the problem is easy. If you have an input, if you have a tile set as input, then the problem there is no algorithm for the problem. So again, it's just a question of what is the input.
For a given set of tiles?
Again, yeah. For a given set of tiles, the answer is either yes or no. So one of my two algorithms, the first one answers yes, the second one answers no, is correct. I don't know which one, but one of them is correct. That's the problem with, again, the fact that the problem is undecidable means that there is no algorithm that works in the general case. For one particular instance, the answer is either yes or no. So it is decidable. But again, I do not know the answer.
The number of tilings is not enumerable. You cannot, I mean, to find one, there is an algorithm.
I am not finding one. I'm just saying that the answer is either yes or no. Again, this is non-constructive.
A no algorithm would mean that the possibilities for these tilings are enumerable. So you have an algorithm which eventually finds it.
Yeah, my algorithm, again, is just inserting yes or inserting no without doing anything. It's just one line, yeah.
So maybe the question was a bit different. Given a tile set, is there an algorithm that produces the tiling?
This is a very different question.
And this is,
okay, yeah. Because now you have an output. Your output is non-trivial. Your output is not yes or no, your output is a tiling. And here the answer is no. This is not possible for some tile sets. So there are some tile sets that exist and for which you cannot say if there is a tiling, you cannot produce a tiling. It's not a decision problem. It's a problem when you have an output. Again, whether there is a tiling or not is decidable for one instance, one particular instance, but you cannot produce a tiling. It's a very different question.
So, do there exist concrete set of tiles, and nobody knows whether there exists a tiling?
This is a different question because now you want to be constructive. Computability has nothing to do with constructiveness. And yes, I can give you a lot of sets. For example, I have 26 of them for which it will be very, very important if you can prove that they tile the plane periodically. Because there will be the smallest possible ones.
But for none of them, those concrete examples, there exists, however, a theorem which says there doesn't exist a constructive method to decide whether there exists. There exists.
I think yeah, there's too many quantifiers in the question. Yeah.
It's like in the word problem, you know, for groups, there is concrete. I mean, the word problem is unsolvable, but in addition, there is presentations with finite many generators and finite many relators, and it's known that for these presentations, the word problem is not solvable.
Yeah, okay, but this is a different problem because now you have an input. The input is the word that you want to know if it is 1 or 0. And this, in this context, the equivalent would be a tile set for which, given a finite patch of the plane, you want to know if it can be completed into an infinite patch. And there exists some tile set for which you cannot decide this. So the tile set is fixed, as you want for a finitely presented group. So your tile set is fixed, and for this particular tile set, even given a patch, you cannot know if it can be completed. So this can be obtained. Actually, if you look at what I've done before, if you look at the collapse sequence, you take this one, you convert it into a tile set, it will have something I did it before. I think you can do it with 12 or 13 tiles. And for this one, knowing if there is a tiling of the plane somehow solves the collapse problem. So knowing if there is a tiling of the plane starting with input n is exactly the same as saying is the collapse sequence infinite starting from n. So this just, of course, this is not undecidable in this case. Well, we don't know, but you can do it with more complicated tile sets and obtain this kind of things. Yeah.
Is there an explicit tile set where you can prove that it tiles a plane, but where you are unable to build an explicit tiling?
We're not able to build one, you mean?
Yeah.
Yes.
Where you have a non-constructive proof of existence.
Yes. So it's not easy to state exactly how you do it, but basically your tile set, I will not give you the tile set, but the tilings with the tile set in each row, let's say, will have 0 and 1, and they will have 0 at each position, 1 at each position n, if, for example, the nth possible formula you can do in arithmetic is true. So this is something for which we do not know any tiling, because one tiling will give you a way to complete the arithmetic into something decidable. So this is the kind of things you have to do. So it's not that easy to give you one, you know, but you can do things like this.